Behind the complex buzzwords of modern artificial intelligence is a foundation of simple mathematics. All of it begins right here, operating inside a single artificial neuron called a perceptron. Our objective is to build, train, and write the code for one of these perceptrons from scratch. We are going to teach it to make a specific decision, whether or not to go on a picnic, based on strict and logic. To do this, we will manually calculate the initial weights of our decision factors. When the model inevitably makes a mistake, we will calculate the error correction. And finally, we will implement the completed logic in Python. Demystifying the mechanics of this single processing node provides the exact blueprint for how massive, modern neural networks evaluate data and make decisions. This animated diagram outlines our perceptron's design. We start by defining two inputs. Input x1 is the weather, 1 for sunny and 0 for overcast. Input x2 is the distance to the park, 1 for close and 0 for far. Next, we assign our parameters. The weights, W1 and W2, dictate the importance of each input. We also add a bias, labeled B. The bias represents a baseline physical energy level, where a negative value indicates being tired and requiring a stronger reason to leave the house. These all flow into a central sum, labeled Z. We process that total sum through the Heaviside step function. The Heaviside step function is a mathematical logic gate that outputs a 1 if a value is strictly positive and a 0 otherwise. If Z is greater than 0, the model outputs a 1, meaning we go on the picnic. If Z is 0 or less, the output is 0 and we stay home. Before the model can make accurate decisions, it needs experience. We provide this through a labeled dataset, which gives the model a specific set of rules to learn from. This chart shows our AND gate picnic policy. Out of 4 possible scenarios, the only combination that results in a target output of 1, a go decision, is when it is both sunny and close. Every other combination results in a 0. Establishing this explicit mathematical blueprint and strict target data transforms the theoretical concept of decision-making into a measurable, testable system. Step 1 is forward propagation. Forward propagation is the process of passing input data through the network to generate an initial prediction. Because the model hasn't learned anything yet, we start with uneducated guesses. We assign both weights a value of 0.5 and set the bias to 0.0. This layout demonstrates testing these random parameters against a critical scenario from our truth table, sunny but far. That is an x1 of 1 and an x2 of 0. Multiplying our inputs by our weights of 0.5 and adding our 0.0 bias yields a total z-sum of 0.5. We apply the activation function rule to this sum. Because 0.5 is greater than 0, the model decides to go on the picnic. This is a mathematical error. Our target data strictly states that sunny but far should result in a 0. The failure occurred because a bias of 0.0 left the model with 0 baseline resistance. It was too eager to trigger a yes based solely on the presence of sunshine, ignoring the long distance entirely. Encountering this specific calculated error provides the numerical difference the algorithm needs to recognize its flaw and begin the learning process. We correct this using the perceptron learning rule, also known as backpropagation. Backpropagation is the mathematical method used to calculate how much each parameter contributed to the error, so those specific values can be adjusted. We apply a learning rate, represented by the Greek letter alpha, set to 0.1. The learning rate acts as a mathematical speed limit, restricting how drastically the weights and bias can change in a single update, so the model doesn't overcorrect. Running the update rule calculates our exact adjustments. The weight for sunshine drops to 0.4. Because the distance input was 0, its weight remains untouched at 0.5. Finally, the bias drops to negative 0.1. In real-world terms, this negative bias means the model has learned to be slightly tired by default. It will now require stronger positive input signals to overcome that baseline resistance and trigger a decision to leave the house. This iterative parameter adjustment is the core mechanical process of machine learning. The system algorithmically turns wrong guesses into calibrated experience. We repeat this update process across multiple epochs. An epoch is one complete pass of the entire training dataset through the learning algorithm. After full training, our perfected parameters stabilize at a weight of 0.6 for sunshine, 0.6 for distance, and a strong negative bias of -1.0. We verify the logic mathematically by running the sunny and close scenario. The combined sum of 1.2 successfully overcomes the -1.0 bias, leaving a positive 0.2. This triggers a correct go decision. Contrast this with the rainy and far scenario. With 0 positive input, the math defaults to the -1.0 bias. The result is less than 0, successfully outputting a stay decision. This generated code editor shows the transition to practical application. We define a Python function for our perceptron decision, pre-filled with the finalized weights of 0.6 and the bias of -1.0. We execute the step by feeding the exact test scenarios from our truth table directly into the arguments of our new Python function. Here in the console output, we see the script perfectly mimics the required AND gate logic. The 1-1 input triggers the let's go print statement, and the 0-0 input returns stay home. Writing the software code is simply the act of translating the mathematical logic the perceptron has already solved into a syntax the computer hardware can execute. We mapped raw inputs to numerical values, manually calculated the error of a random guess, updated our parameters using the learning rule, and successfully verified the trained model in Python. This side-by-side diagram highlights the direct one-to-one alignment between the theoretical mathematical equation on the left and the practical code syntax on the right. Now, open your own code editor. Adjust the target training data to create an OR gate policy, teaching the model to go on a picnic if it is sunny or close, and calculate the new weights yourself. Mastering the mechanics of this single perceptron empowers you to manipulate the foundational building blocks that underlie all artificial intelligence systems.